Maybe we wait for another 2 more minutes. Okay, can everyone hear me? Is it clear or not?
Clear.
Yeah. Okay, thank you. So if you can't hear me, just shout out. If you have any question, you just shout out. Okay. Okay, we'll continue from this afternoon. So next part we'll talk about is to find the arc length of a plane curve. So what's the arc length? So an arc length of a plane curve. Okay, let's say our curve is given by two functions. Okay, x equal to ft and y equals to gt for a period of time from A to B. Okay, so what's the arc length? It's equal to the integration of A to B square root dx dt squared plus dy dt squared over dt. Okay, let's say if this formula doesn't make sense to you, so let's draw a picture. Okay, let's draw a picture. Say we got our xy plane, okay, and then we got a particle moving around like this. So we want to find the length of the arc. So we call it arc length. Okay, we call it arc length. So a priori, we only know how to measure straight line. Okay, so we can use straight line to approximate the curve. So for example, any question? Okay, so we can approximate. Sorry, we can approximate the curve with a few straight line. Right. Okay. Let's say we cannot. Tổng Jie, is it? Tổng Jie. Can you mute your? Thank you. You can turn on your mic if you want to ask question, or you want to put inside the chat also can. Right. So let's say you cannot bend your ruler, right? So how many times you need to measure this curve? So you can make your ruler as small as possible until you can measure the actual curve of this, actual length of this curve, right? Another way to think about it is another way to think about this formula here is the Pythagoras theorem. Okay. So what does Pythagoras theorem tells you? So if you have A and B as two sides of your 90-degree right angle triangle, then you can compute the C. So if you know the change of X and the change of Y, you can compute the length of the hypotenuse, right? So C square equals to B square plus A square plus B square, okay? And C is just the square root of B square plus A square here, right? So you can see that this square root thingy is really similar to the Pythagoras theorem, but we have an integral here because we are taking some form of limit when dx and dy getting small, okay? Furthermore, these dx and dy are depending on t, okay? All right. Please stop me if I'm too fast, okay? Because I can't see your face. Do you want to prove this, or you are happy with this idea how this formula come from? You want to prove this? You want to see a proof? What's okay mean? You want to see the proof, or you don't want to see the proof? Anyone want to see the proof, or we go to computation? Want to see a proof? Okay. Sure. Okay, let's prove it. So the idea you can see from Pythagoras theorem, and then also we want to make our ruler as small as possible so that we can really compute each length of our curve. Okay, so how to prove it? So let's prove it. Okay, so prove it. Okay, so so you can see from Pythagoras theorem, right? So let's say we label this point as P1, P2, P3, P4, P5, P6, and so on. Okay, we can see that the difference between Pi minus 1 and Pi is the square root of the change in X. Maybe I should write, okay, I just write change in X square plus change in Y square. Okay. For now, you really can regard these two as the same thing. Right, this one is by Pythagoras theorem, right? Yeah, by Pythagoras theorem. Okay. So how should we relate to t? Okay, how should we relate to t? So we are given that x is a function of t. Okay, y is also a function in T. Okay. Furthermore, actually, we should say that F and G are actually continuous. So to sketch out a plane curve, you need a continuous function, right? Otherwise, your curve will break. So actually, you have continuity in your F and G. So in this case, uh, in this case, mean value theorem apply. Okay. So why we like mean value theorem a lot? Because the theorem can help us to relate the point on the function to its gradient. Okay. So for example, we get FTI minus FTI minus 1 equals to the gradient of f prime at some point where this point is in between Ti and Ti minus 1. Okay, and then multiplied by Ti minus 1. I'm not sure how familiar are you with mean value theorem. Maybe I just briefly talk about the idea of mean value theorem. Okay, so if you rephrase this mean value theorem, I mean rearrange it, what you get is really what? Really a gradient, right? This is gradient, right? So you have difference of 2y over difference of 2x. Okay, so you are getting some gradient, but can it be a gradient of that curve? Okay, so the mean value theorem tells you that it is the gradient of that curve applied to maybe some other point. Okay, some other point in between Ti and Ti minus 1. Okay, so what should you think about it? How should you think about it? So pictorially, really you need to think about it geometrically. So this is your curve. Okay, so let's say this is FTI and this is FTI minus 1. Okay, so maybe I switch my time first. So from Ti minus 1 to Ti, okay? And then taking the ratio of this thing here, okay? So you're taking the difference. Okay, let me use another color. So what are you really doing is you compute this straight line here, gradient of this red line. So let me point this red line to this number here. So you take the difference of y over the difference of x. Okay, right. So here is the dy, here is the dx. Okay, so what does it mean by you are equal to sum of the tangent at a certain point in between Ti and Ti minus 1? That point is exactly around here, okay? Where you can just move this f prime up. Okay, so it is realized by some point in between Ti minus 1 and Ti. So let's call it Ti start. Why can you do that? Precisely is because your function is continuous. Okay, if it is not continuous, then maybe your function break at some point where you don't achieve this point. If it is continuous, at some point they have to turn back. When you turn back, you must pass by this gradient at some point. Okay, makes sense. So this is mean value theorem. Okay. All right. Does it make sense? Mean value theorem. Any question on mean value theorem? Okay. Okay, good. Okay. So by this mean value theorem, what do we get actually? Okay. So what is ft minus ft minus 1? Okay, this is our x. Remember, this is our x. Our x is defined by a function f. Y is defined by a function g. And both of them are continuous. So this is I couldn't say hidden. Actually, plane curve need continuity in your function so that it sketch out a curve without breaking. Okay. So continuous curve. Where are we? Okay. So next we get the delta xi equals to f prime ei star at a change of t. Okay, we make the difference into delta, the change of xi and change of t. Okay, so similarly, because g is continuous, right? So we can get a similar equation for delta yi, which is g prime ti star star. Okay, maybe it's a different time, so we put ti star star time delta t again. Okay, so we fix the time interval, and then we look at the change of delta xi and delta yi. Okay. So what is f prime? F prime ti star. Okay. So fi ti star really is dx over dy over dt, and g prime is, sorry, dx over dt, dx over dt, and dy over dt. Okay, so here don't confuse with the dx I wrote just now, right? So this is the operator differentiate x with respect to t, differentiate y with respect to t. Okay, just now I wrote dx dy is just change in x direction and y direction. So we have this, okay, and then we also have this Pythagoras theorem together. Right, let's move this down, copy, paste here. And then maybe we bring this picture down as well. Okay, sure. So let's bring this number in. So what do we get? So I think I do something stupid again. So let me change it. So let me move this. Okay, let me rewrite this. Okay, let me try and put this. Yeah, this is correct. Okay, I think this is correct. Let me see. Did I do something stupid? Okay, sure. So let's keep going. So let's substitute the number in. So d over dt x delta t squared plus d over dt y delta t squared. Okay. Okay. So then, since both of them have delta t, we can move the delta t out. Right. Move the delta t out from the square root. Okay. So this is the length of a piece of P1 to P2. Okay, it's the straight line from P1 to P2 or P2 to P3 and so on. Okay, for all I. Right. multiplied by t. Okay, then what's next? What's next? Next, we need to add up all the straight line together. Okay, we need to take the sum of them. Okay, we need to take the sum of them, and then we need to make it to infinity. Okay, so we need to add arbitrarily many points so that we can infinitely approaching the real curve. Okay, when we add more and more interval into this line, the straight line will keep approaching the curve. Does it make sense? Let me write it down. So the real curve is when you add in arbitrarily many interval into your point. Okay, so you get more and more little small ruler to measure your curve, right? If your ruler is too big, then you might miss some of the curve section. So you should make your ruler smaller and smaller to approximate every part of your curve, right? And then you add all of them up. So you take a limit. And then multiply by delta t. Okay. And then so what's this limit of sum, finite sum? This is really the integral, the definition of integral. So integration is approximating infinitely many time. Any question or not?
So can you move upwards?
Upwards? Up, you mean like this? Up?
And up a bit.
Up a bit. Okay.
How do we know that we need to define x equal to the function ft and y equal the function gt?
Okay, so remember the parametric equation, right? Our x is in terms of t, y is in terms of t, right? Is that right?
Yes.
Okay, so if you don't want to write ft, that's fine. You can write xt and yt. It's the same thing, really. We are just saying that x is equal to some function in t. Or you say that x is a function in t. They are both same thing. You get what I mean? So let's say, okay, let's say for example. So for example, st is equal to 2t, then ft will be equal to 2t. This is the definition of parametric curve or plane curve. It's defined by two parametric equation. We want to measure the length of a plane curve. So our xy are given function in t, continuous function in t. Does it make sense?
Yes, makes sense.
Okay. Okay, good. Any other question? Let's say if this proof doesn't look appealing to you, let's do some calculation first. Okay, let's do some calculation to convince ourselves this formula is actually useful. Okay, let's compute the arc length of the following curve. So we talk about curve, right? Plane curve. Okay, so we need to have two parametric equation. So let's look at x equals to cos t, y equals to sine t. Okay, where you take time from 0 to pi. Okay, does this look familiar to you or not? This curve. Does this look familiar to you? This curve here. What's this curve? Does anyone know?
Circle, circle.
Yes, circle, but not a whole circle, right? It's just, where's the circle? I mean, this is not a circle by right. Because the time is only from 0 to pi.
Half, half.
Okay, so it's the top hemisphere. Okay, it's the top hemisphere. From t equals 0 to t equal to pi. Okay, this is a unit circle. I think you should know what's the circumference of this. I mean, not circumference, the length of this this curve, right? Does anyone know how to find the length of this curve without doing integral first?
Pi r.
Pi r, you sure? Oh, semicircle is pi r, right? So full circle is 2 pi r, so you divide by 2, you get pi r. So the r in this case is a unit circle, r is 1. So it is just pi. Okay. So our answer should be pi, so that it shows some usefulness, at least for this example. So let's do it. So by definition, okay, so by definition, L is equal to the integration from a to b square root. Okay, remember where the square root came from? The Pythagoras theorem. Okay, Pythagoras theorem. Square root dx over dt square plus dy over dt square dt. Okay, so I think dx over dt is just minus sine t squared plus cos t squared dt. Okay, so I think by this trigo identity, cos square plus sine square equals to 1. And dt, we will get square root 1 dt. So where are we integrating from? We are integrating from 0 to pi, actually. Okay, so we are integrating t evaluate from 0 to pi, which is just pi. Okay, so we get what we wanted. Right? Make sense? Yeah, I think, yeah. No comment. Any comment before we go to the next part?
All good, all good.
All good? Okay. All good. So next, we go to the next part. We find area. So next part, we will find the area under the curve. Okay, so similarly, we have, okay, so let's write our area as A first. So the area A under the plane curve. So I repeat again, plane curve, we have two parametric equation. So x in terms of some function t in t, and then y as a sum function in t. Okay. If you don't like, you can just keep xt and yt. That's fine. So t, we have to have some bound. Let's call it a and b on the left and then on the right endpoint. And also, in this case, we want our gt to be positive. I'll comment later why we want gt is positive. So the area will be given by integration from a to b gt f prime t dt. Okay, so let's see how we make sense of this formula. So let's draw a graph again. Okay, so in this topic, right, you should keep the xy plane fixed in your mind, and then have some plane curve. Okay, let's say like this. So let's say here is t equals to a, t equals to b. Okay, and gt is positive, right? So here gt is positive. That's why it lies on the top, the first quadrant, positive. And then let's say we want to find this piece of area. So I think from your calculus 1 or either high school, you should know how to find area under the curve, right? So how do you find it in terms of x, y? You should integrate the y function with respect to dx, right? Okay, let me just write out. So you should integrate from FA to FB y dx. Is that right? Am I doing something stupid? So where's FA and FB? Okay, remember our x is controlled by F. Okay, so the starting point is FA, the ending point is FB. Okay, so you integrate over this x interval, okay, and then following the y over dx. Okay, I think this is the usual area under the graph, right? But our x and y is in terms of t, so we want to make this formula here in terms of t, so that we can really do some direct computation, right? So we need to do change of variable. Okay, we need to change from x to t. Does it make sense? We want to change from x to t. Okay, so we need to do change of variable. So change of variable x equals to ft. So in this case, our dx become f prime t dt, right? By chain rule. Okay, and when x equals to fa, right? When is our t? Our t is just equal to a. And when what x equals to, so when x equals to fb, our t is equal to b. Okay. So in this case, the integral becomes integrating from a to b, and then y is equals to gt, and dx after change of variable become f prime t dt. Okay, so that's why there's a derivative coming up in the integral here. Okay, because you do a change of variable, and then this gt is really the y here. Okay, before we go into example, does this make sense? Does this definition make sense or not? Any question on this definition? Any question? Yes? Yes, yes, you mean you got question or what? You want to open your mic? No question? Okay. Okay. So just now I said that I want to comment about this this positive GT, right? Okay. So really, when you integrate area under the curve, there's this orientation on this curve, okay? Because the time, like I say always, the time induce a orientation on your curve. So really you integrate over this curve with the orientation, the area under this oriented curve. Okay, let's say if my curve go the other way, then this area might change to negative. So there will be a sign different. Okay, so if you like, you should please Please read on Adam on the sign change of A, sign change of A due to orientation. Okay. I think maybe not so important for this course, but I think it'll be useful later on. Maybe you can have a read and then let me know what you think. Okay, should we do one exercise on this? So let's try with an exercise example. Okay, so find the area A under one arch of the cycloid. So this particular curve, we call it cycloid, which is the one I asked you to derive last time. I will pull out the solution. So let's say these two parametric equations are given. Okay, so we want to find area under one arc. What does this mean? So let's draw this curve first. So whenever we talk about curve, make sure we can draw it. So this is y and x. So a cycloid will be looking like this. So the question asks you to find area under one arc. Okay, let's say this is going from 0 to 2 pi r. Okay. All right. So you can see that this range here is given in x, right? So we still need the range of theta. Okay. So how to find it? So let's check when x is 0. What is our theta? Okay. We get 0 equals to r times theta minus sine theta. So which means sine theta equals to theta. Okay. So this is kind of hard. When does sine theta equals to theta? When does sine theta equals to theta? Anyone have any idea? When does sine theta equals to theta? So maybe we can 0. 11 says 0. Okay, so if you look at the sine curve, let me see a sine curve. So here is pi, 2 pi, 0. Okay, so sine is bounded by 1 and minus 1, right? Okay, and the curve is not straight at all. So really, when you get sine theta equals theta, theta can really only be 0. Okay, at 0 it's easy to check because you just check that sine 0 is 0, and then you need to rule out any other cases by reasoning on the curve. Okay. Okay. So what's the other point? So when x equals to 2 pi r, what's the angle? Okay, now you can see that somehow this this function gets shifted, right? So instead of sine theta equals to theta, we want sine theta equals to theta minus 2 pi. Okay. So when is this true? When is this true? So sine theta, the curve sine theta, need to equal to the angle minus 2 pi. When is this true? Yes. So it's 2 pi. Okay, good. So when theta equals to 2 pi, you can see that sine 2 pi equals to 2 pi minus 2 pi. Okay. You can see that actually really the whole curve gets shifted by 2 pi. Okay. So the 0 point become the 2 pi point. Okay. What's next? So next, let's write down what we need. So we want to compute by definition of area. Okay, so area is equals to integrating from A to B, starting point to end point of G theta F prime theta D theta. Okay, so we got A to B now, right? So we get from 0 to 2 pi. G theta, do we have it? We have it, right? So it's the R, it's the Y, sorry. So this is our G theta. So let's put it down. R1 minus cos theta. But we still need F prime D theta. Okay. So we got our F prime, but we not yet get our F prime theta yet. So what's F prime theta in this case? It is just R times 1 minus cos theta. Okay, so then we can plug this fellow in. So it is R times 1 minus cos theta again, d theta. Okay. Yeah. So what do we do? So we just multiply all of them together. So you get R square 1 minus 2 cos t plus cos square t dt. Okay. So we can't really integrate power of cos, right? We need to make it into a cos function. So there's a trigo identity again, where we can transform cos square theta into 1 plus cos 2 theta over 2. Okay, so in this case, we can transform the power of cos into some function of cos with a different period. But that's fine. We know how to differentiate it as long as it is a cos function. So let's keep going. So R square is our scalar now, and then we make cos square theta into 1 plus cos 2 theta over 2, and then d theta. All right. So what's next? So next, we just integrate term by term. So let's move the R square out. It's just a scalar. And then 1 become theta. So let me just write like this. 1 become theta. So cos theta become sine theta. And then half become theta over 2 plus integrate cos 2 theta. What do you get? You get sine 2 theta, but divide by 2 again. Evaluate from 0 to 2 pi. Okay, what's this whole thing here? You can try and calculate it yourself. You will then get 2 pi plus pi, which is 3 pi r squared. Okay. Okay, any question? Should we take a break or continue? I think you guys are quite relaxed, I think. Or you want have a toilet break?
Break.
Okay, so let's break until 6:57 and then we will go into surface area. Maybe you guys can turn on the video if it is convenient for you.
We are too shy.
Too shy. Why not you open? Yeah, this online teaching remind me of the time of COVID when I was the tutor. We do tutor online as well because that time has quarantine. So the student all turn off their video, so you're like talking to a black screen, and then they also talk you back with a black screen. So it's kind of horrible and scary.
Oh, don't worry, I won't leave you alone.
I mean, yeah. Hey, who is this Chen Zhen Xuan? Huh? Seems like you are not as active in the class. Chen Zhen.
I shy ma, shy.
Okay, I must know you next time. Yeah. So that's why I skip tutoring during the okay. I think in Malaysia called MCO, right? The quarantine period. Yeah. And also hard to control the class online.
So do you teach linear algebra before?
Yeah, I teach last semester short sem. They do the linear algebra in 5 weeks and almost finish the whole book. I think it's crazy. Even myself also don't finish up to the. Did you learn up to the what singular value decomposition? Or you
What
guys
is that?
sorry, chapter
What is
7 I think. Is it covered?
decomposition?
Yeah, singular value decomposition. I think
I
it's
think
chapter 7. Do you guys cover until that topic?
I think we learn QR decomposition.
Oh, I think that one is quite I mean at the end you will learn something singular value decomposition, I guess. Wait, what linear algebra? First of all, is this the Liu Jie one? The second one, is it? I only teach the first one.
Yes, the second one.
Oh, the second one. Yeah, I'm not sure what's in there. By the way, next week everyone should give me the title of project. Either you started or you haven't. Okay. Cause you only left with 1 month, so at least you have some idea. But you still can change the title if you like in the middle of the time. But next week I want to get title from everyone. So I think most of you, I'm not sure it's most of you or not. Some of you told me that you're not sure how to start. So I will recommend that you pick from what you like. So do you like number? Do you like function? Do you like geometry? Or do you like algebra? And then from there you can kind of pick and choose. Okay, let's start and then we will talk again. Okay, next part is this surface area. Okay, this is similar to what we did before. But this surface area, what's this surface area? So you take a plane curve, okay, and then you evolve around the x-axis. Okay, so you take your plane curve and then evolve around x-axis 360. So if it is a straight line, right, you should imagine that this trace out a cylinder. This is what you should imagine. Okay, you trace out a cylinder. Okay, but note that our curve can be quite curvy, right? So you can go all the way you like. So you take this curve and then you evolve around x-axis. Similarly, you can evolve around y-axis, but let's talk about x-axis first, okay? So the definition is the area of the surface obtained by revolving the parametric curve similarly defined by two equations, okay? Your coordinate continuous given a time limit f to b. So what's this? How does this define? Around so about the x-axis is x equal to integrate from a to b 2 pi y square root the dx over dt square plus dy over dt square. Okay. So why is this? So why is this so long? This formula here. Okay. So how to make sense of this formula? All right. Okay. So how to make sense of this formula? So can you imagine what's the radius of this cylinder? Let's say we got this cylinder here, right? So what's the radius of this cylinder? Anyone have any idea? What's the radius of this cylinder? What's this yellow thing? X or Y control the radius? Hey, I saw something in chat. Sorry, I missed out. Y. Okay, good. Okay, so Y control a radius here. If I miss something in the chat, please call out. Okay, so Y control the radius. So how you find the radius of a cylinder? What's the formula of the surface area of a cylinder? Surface area of a cylinder. How do you find it?
2 pi RH.
Good. So 2 pi RH. Okay. So h is the height, r is the radius. So we know the radius yt now. But what's the height? Okay. So what's the height? So the height is this. Wait a minute. So this dx, we call it dx just now, which is the length, the arc length, right? Okay. So this arc length form your h. Okay. Depend on how long is your curve. Okay. So you can see that this, for arbitrary plane curve, this cylinder is irregular, right? Irregular. So something irregular, right? We need to pass to limit. Depend on dx. Depend on dx. Is that right? Depend on this s. Okay, I mean this s here. Okay, not just this x. This s here. So depend on this length. Okay, so it depends on this length. All right. So really, if we pass to so the normal cylinder will get 2 pi y dx, right? So the length of the curve. But since this is irregular, we need to pass to the differentiation integration of dx. Okay, so let me put a prime b prime here. Okay, so we need to pass it to the variable t. Okay, remember what I'm doing. So actually I'm substitute dx equals to square root dx dt squared plus dy dt squared dt. Okay, so I make this a change of variable. Okay, that's why you got this big chunk of square root coming in due to the length of the irregular curve. Okay, arbitrary curve. Okay, so okay, so let's put this into practice. So let's put this into an example. Okay, so let's talk about the surface area of a sphere. Okay, so how do you make out a sphere? A hemisphere is enough to make out a sphere. Okay, by revolving it around a x-axis, about the x-axis. So if you rotate the semicircle, okay, so semicircle come back again. So x equal to r cos theta and y equals to r sine theta. When you control it between 0 and pi, okay, about the x-axis. So find the surface area. Area of the sphere with radius r. So arbitrary radius r. So okay, so really we should draw out the picture. Okay, we should draw out the xy plane. And then look at our plane curve, which is the hemisphere, the top hemisphere. Then we do rotation around, revolving around x-axis. So you trace out a sphere. So can anyone remember what's the formula for surface area of a sphere? Before we calculate.
4 pi r square.
Okay, good. So if this formula gonna work, we're gonna find 4 pi r square. Okay, so let's take the formula. So x is equal to integrating from a to b, 2 pi r, your radius, so here controlled by t, and the dx, which is the length of your curve. So the length of your curve, remember the Pythagoras theorem. So you have a square root of dx over dt square plus dy over dt square dt. Okay. So now our time is going from 0 to pi. 2 pi. Yt is r sine t. Okay, I think we compute this dx dt long time ago. which I think we get r square. Sorry, just put r minus, so minus r sine t squared plus r cos t squared dt. Okay, so what do we get? So we get 2 pi r sine t. So you can combine using the trigo identity again, where you left with square root r square, which is r dt. Okay, and you can move all the 2 pi r square out, move all the scalar out, and then you integrate sine t from 0 to pi. Okay, so what is integrating sine t? You get cos t, or minus cos t actually. So integrate from 0 to pi. So what's this? This is really minus of -1, and then minus, why am I putting -1 there? So cos pi, what do you get? So let's draw this out. So here is pi. Cos pi is -1 minus cos 0 is 1. Cos 0 is 1. Am I doing something wrong? Cos pi is -1. Cos 0 is 1. Do you get 0?
So there is a
Ah,
negative here because the negative
wait.
cosine t. So it's minus
Wait.
minus 1.
Cosine t. Oh, right. You are right. Very good. Very good. So it's a minus minus t. I was wondering where the other minus coming in. So let's move this away. So we got a minus minus 1. Okay. So these two minus coming from different places. So this minus coming from the original minus. This is the integration minus. And then this minus is coming the same reason as this minus. Okay. So this good. So we got 4 pi r squared. Okay, which is what we want. So we wanted the area of a sphere is 4 pi r squared. Okay. There's a question in the example. I mean, not example. Yeah, in the previous lecture note. So that one we will left as an exercise. I'll provide solution as well. One question in a previous year note left as a homework. I'll provide the solution later. Okay, so what time is it? We need to go into the real business. Okay, 7:10. Good. Okay, so so we just now talk about circle, right? We keep talking about circle. So really, instead of describe our point using xy, okay, there's another way to describe our point. Okay, using r theta, radius and theta. Okay, before talking about this, so you can see the xy is kind of what we call, okay, let me write down the name first. So these are called the Cartesian coordinate. I hope you have heard it before. Okay, so Cartesian coordinate. So usually we call this a rectangular coordinate. Okay, so Cartesian coordinate, you can think of it as this discrete point here, right? So every point on xy plane are characterized by X and Y. Okay. So there's another way you can characterize this plane, right? So instead of looking it as a discrete point, you can okay, I don't want to draw r theta here. Let's put xy again. So you can use a circle to differentiate every point in your space. Okay, so we call this stratification. So we can stratify this space differently, right? So every point, okay, every xy point must lie in one of these circle. Does it make sense? Okay. Instead of go up, go down, go left, and go right, you can go radially. Okay, so you can go radially. Right. So for example, what? For example, um, let's give you an example. So let's look at a circle point, right? Yeah, so let's look at the unique circle. A point line on the unique circle. So let's call it, what's this point here? So in XY form, what is it? Let's say this is a unique circle. Okay. Maybe I just make it bigger then. Resize. So this is a unique circle centered at 0, 0. Okay. So I look at the intersection with x-axis. So this point is really 1, 0, right? Okay. But I also can describe it in another way using radius and angle. So I can use r theta to describe it. Okay. But these two are really the same point. So if I write it as r theta, maybe I change this color. So different way of writing it. So r theta is radius 1 and theta 0. Okay, it turns out to be the same. Okay, it is a coincidence. Sorry, this is a coincidence. So it can be different. It can be different, right? So let's pick another point. Okay, pick this one. So let's call this x1, y1, and then this one r1, theta 1. So at the other point, x2, y2 is equal to 0, 1. Okay, but I also can express it as r as 1 and then theta as pi over 2. Okay, so what can you see here? Our angle is really starting from the x-axis, positive x-axis, and then revolving anti-clockwise. So anti-clockwise. Okay, 0 to 2 pi. So when it is 2 pi, it come back to the same point. So we regard theta and theta plus 2 pi are the same point. Okay, in the radially world. So we will call this actually, there's a name. So we already know that this is a radial coordinate, so we call it a polar coordinate. Okay, using r and theta. Okay, so similarly, actually, let me make these smaller a bit, resize. So there's another way to draw this xy plane. So you can just take your radius, axis, okay, which we call the polar axis, and take a point here, which we call, let me see, what's the name? We call this pole, okay? this thing we call pole. Let me use this. So we call pole here. Okay. So you can think of it as the have you used have you fill in the gas? What's that thing called? You fill in the gas of your tire or fill in the gas when you pump your tire or you pump your balloon, right? You can see the needle like moving, right? So this is exactly what similar to those needle moving, right? So when you have this radius, radius is always positive, right? So okay, let me label this. So here is the origin, okay? So your radius is always positive, so you can go forever positive, okay? And then you can move your radius 2 pi around so that you can reach every point in your xy plane. Does it make sense? Does it make sense? Does it make sense that every xy plane, xy point, I can label by a radius, okay? The length from the origin, okay, and the angle with the positive positive x-axis. Okay, so let me write up. So let's say we have this point here, xy. Okay, so this xy is characterized by the radius and the angle with the positive x-axis, which we call the polar axis. Okay, so to think about this polar axis, you can think of the pump. Okay, when you pump the tire, the needle will move, right? But this radius here can grow as long as possible to cover the whole plane. Does it make sense? Anyone have any question here? Okay, maybe we continue first. Okay, so another comment is when we go around 2 pi, right, it come back to the same point. Okay, so when you keep going around 2 pi again, is still the same point, right? Okay, so meaning that from 0 until not including 2 pi, it is enough to describe every point in the xy plane. Okay, so inside xy plane, it is an angle from the positive x-axis and how far the radius, okay, is enough to describe. It's equivalent. But we will see in a moment why these polar coordinates are more useful sometimes. Okay. So so there's a question. So given xy, how you go between r theta, right? Given an point in xy, how you go to r theta? How you find the radius and the theta? From this picture, maybe. Anyone have any idea?
X equal to r cosine theta, right?
X equals to r cosine theta. Yes. Okay. So you can see that you can see from this picture here. Okay. See from this picture here. If you can draw this right triangle, this horizontal part is the x coordinate. Okay. So y coordinate you need to use sine, and then x coordinate you need to use cos, right? Because this is adjacent to this angle here. And then r is the hypotenuse. So exactly you are right. So x, when you want to go from Cartesian to coordinate, polar coordinate, so you need to make x equal to r cos theta and y equals to r sine theta. Okay, actually better is going this way. So given r and theta, given a radius, given angle, you can find your point in xy, right? Okay, so another question is, since this is equivalent, right, we should be able to go from the right to left and left to right. Okay, so let's say given x and y, how we find r and theta? Okay, so here we go from right to left, so we can go from the left to right. So how to find r and theta? Anyone have any idea? Since these two are equivalent, so equivalent. These two are equivalent. Just now I explained pictorially, right? Now we need to do it algebraically. So algebraically, what is r and theta in terms of xy?
I think we can use the tangent to find theta, right?
Tangent to find theta. So how?
Like y divided by x is tangent.
Y divided by x. Okay, so let's try out. So let's try. So y divided by x is r sine theta over r cos theta, which is tangent theta. Okay, right? So use y over x, we can find tangent, okay, because we can just take the inverse of tangent, right? So how about r? Any equation that need to be satisfied by r or not? There's a trigo identity, we keep using it. So these sy have to lie on a circle, right? Okay. What circle does xy have to lie on? What kind of circle? What kind of circle does xy have to lie on? So give you a point in xy. So what kind of circle does this point need to lie on? Pythagoras theorem? Are you answering me or what? What's Pythagoras theorem? Can you explain a bit? What's Pythagoras theorem? So given a point in xy, how do you determine which circle it has to lie on? I think you need to be able to see this before this this section will make sense to you. Given a point in xy, determine a circle that it has to lie on. Radius of r, good. Okay, so you see your x is equal to r cos theta, y is equal to r sine theta, right? So if you take x squared plus y squared, you get r squared of cos square theta plus sine square theta, which is just 1. So it is r squared. So your s squared plus y squared need to be r squared. Okay, so in that case, if you take square root, then you can find your r. Okay, make sense? So going from polar to going from Cartesian coordinate to polar coordinate, really you're asking which circle you are lying on. Okay, this circle is not arbitrary circle. This circle have to be centered at 0, 0, the origin. Okay, so what changed is only the radius. You need to be able to see this before this section will make sense to you, okay? Okay. Any question about these or not?
So why arctangent equal to y divided by x instead of tangent theta equal to y divided by x?
Okay, so I should remove this. Okay, because I put tangent on the different side, so I should. If I put on the y over x, then I put inverse. Yeah, thank you for correcting. A side question. Do you know this Cartesian? Where this name come from?
Scientist.
Scientist. Okay. This name this is coming from a French philosopher or mathematician called Rene Descartes. I think Descartes. Okay. So he got a famous phrase. He said that I think, therefore I am. Okay. Why he exists? Because he think that he exists. He doubt that he exists. So I think, therefore I am. Very famous phrase. Okay. Next. So so we can extend our polar coordinate. So we extend the polar coordinate. So what do I mean by extend? So just now we say that it's enough to use positive radius and 0 to 2 pi to describe every point in the xy plane. Okay, but sometimes it is useful to introduce a minus radius. Okay, minus radius. So what do I mean by minus radius? So let's keep our polar axis up. Okay, I want to be I want to remind you that this polar coordinate is still working on xy plane. Okay, so don't confuse with don't confuse with xy coordinate and polar coordinate. They both work on xy plane. Okay, just that the polar coordinate is a different way to describe the point. Okay, I don't want you to confuse with these two. So we always work on xy plane. So in your mind, you should have some uh xy axis in your mind. So so let's say this point is r theta now. Okay, we describe it as a r theta. So what do we mean by minus r? So you can see that this line extend. Okay, this line extend. Then we will define minus r, which is going to the other direction. Okay, and the angle here should be pi. Okay, really they lie on the same line. Okay, but opposite direction. So in this case, we will call it minus r theta again. So what's the theta here? Theta is the basic angle here. Okay. Does it make sense? Does it make sense? Okay, so why we have this minus r? Because we also can have minus theta. Okay, minus theta I think is quite more intuitive. Okay, so what do we mean by minus theta? So let's do the same game here. Do the same game. Okay, let's do the same game. So where's this dot from? So minus theta should go down, right? So theta going anti-clockwise, minus theta should go clockwise. So use green. Go here. R minus theta. Okay, so here is minus theta. So if you take minus theta, it go clockwise. Theta go anti-clockwise. Both of them start from the positive x-axis. So you must remember that we start from positive x-axis. Okay, and then if you take minus r, so in this case, so let's apply the minus r convention here, right? So resize. So if we take minus r minus theta. Okay, so this means what? This means we extend the point r minus theta and then go the other direction. So we'll go this direction. So here is minus r minus theta. Okay. Let me move out a bit. So there's one thing to note here. See, r theta and minus r theta here, right? So you can see that this angle here, really, it is theta plus pi, okay? But we don't record it down. If you like, this is actually also r theta plus pi, okay? So this is the definition, okay? R theta plus pi equal to minus r theta. So why we prefer this here? So this means that this is the opposite of r theta. Okay, does it make sense? When we put minus on r, it is the opposite of r theta. Make sense?
Yes, super sense.
Makes super sense. Okay, very good. So another thing is still you need to remember that theta is equivalent. So this is equivalent to theta plus 2 pi. Okay. So meaning if you go, let's say, if you go from okay, let me use another color. So if you go all the way and then come back again, okay. So these 2 points are actually the same. Okay, theta plus 2 pi. So this is a bit too long. So let me remove it. So here. Okay. So this one equal to r theta plus 2 pi. I think this is all the relation you need. Okay. Yeah. Okay, so for now maybe we can do up to here. Okay, let's try some example out. So try and find, so example. Try and find the Cartesian coordinate for 4 pi over 6. Okay. So what's 4 pi over 6 means? So this 4 pi over 6 lie in what circle? Circle of radius what? 4 pi over 6. Right, this is another r theta. So what's the radius of the circle it lies on? 4. Okay, very good. So it is 4. So let's draw the circle. And then radius 4. Okay. So remember, polar coordinates, Cartesian coordinates, both are on xy plane. Okay. If you like to draw in a polar axis, also can. Okay, personal preference. But I would like to remind myself I'm still in xy plane, so I would like to draw xy. If you want to draw this picture, it's fine as well. Just remember you are still in a xy plane. So where's pi over 6? Okay, so 0 here, pi over 2 here, pi, and 3 pi over 2. So pi over 6 is in the first quadrant. Okay, so somewhere around here. Somewhere around here. Pi over 6. So the intersection is the point we want. Okay, good. So now, please find what is x and y. Okay, your turn. Let me see what's the time. I give you 2 minutes. See if you can figure out what's the xy for this point here. how to describe it as Cartesian coordinate? What's the x component and what's the y component? Anyone can find what's x and y? What's x and y?
I think it's 2 square root of 3 for x.
Okay. Yeah. Y is.
I think it's 2.
Okay. So what did you use?
R cosine theta and R sine theta.
Okay. So you need to send your point r theta to xy, right? So what is x and y? So x is equals to r cosine theta and y is equal to r sine theta. Okay. So you just plug in your value, which is 4 cos pi over 6, 4 sine pi over 6, which is 2 cos 3, then 2. Okay, so actually you don't realize, right? This is really the orthogonal projection, okay, to x, and then project to y. Okay, if you want to see it that way, it's a orthogonal projection. This r cos theta and r sine theta. Okay, anyone have any question or not? Does anyone have any question? If not, I have another question. So let's say I want to write it as minus r, okay, minus 4, right? What's the equivalent way to write this point here? So what's the angle I should put if I want to write as a minus 4 as the radius? What's the angle I need to put here? Anyone have any idea? If I want to write it as a different,
Pi,
huh?
pi over 6 plus pi.
Yes, pi over 6 plus pi. Why? Okay, why? Because if I extend this line here opposite, so I need to compute what's the angle here first, right? Okay, and then this here is 4 pi over 6 plus pi. Okay, then to go opposite, I just take the minus radius. Okay, so to get back the same point. So in this case, I get minus 4, 7 pi over 6. Okay. Anyone have any question or not? Okay, I still want to write this point as another way. Okay, so what if I make my angle clockwise instead of anti-clockwise? What can I write? Let's say I want to go clockwise. Let's say I want to compute clockwise, so meaning minus theta. Okay, so what kind of angle I should take? If I want to go minus theta. So if I want to measure this point from a clockwise orientation. Any idea? It's still positive, but I want to go clockwise instead of anti-clockwise. If I go anti-clockwise, I need to get this angle, right? What's this angle? What's this angle here? Oh, 2 pi minus original angle. Yes, correct. Yeah. So 2 pi minus pi over 6. Okay, but this is not enough, right? Because I need to go clockwise. So going clockwise, I need to put a negative. So what do I get? 4 and 11 pi over 6. So negative. Okay. So 4 negative 11 pi over 6. And pi over 6. Okay. Similarly, I let you try and think about this. So I also can write minus 4 of minus 11 pi over 6 plus pi, which is minus 4 minus 5 over 6. Let me think. Am I right? Oh, I don't plus pi anymore, just like this. Okay, just like this. Okay. So there should be 4 equivalent way to write polar coordinate point down. So let me label them. Wait, let me check. Okay, so I think I should plus pi. So let me add a pi. So please check whether this is true. But what is true is we have 4 way. So one first way, second way, third way, and then the fourth way. Okay, so you can see that one of them is all positive, one of them is negative in radius, the other is negative in angle, and then the other one is both have a negative sign. So these are the 4 equivalence where you can describe a single point xy in polar coordinate. Any question? Oh, good. Okay. So please check my blue answer is correct or not. I will put it up soon. I will also check my answer later. So we will be ending soon. So let's introduce polar curve before we break off. Okay, so what's the point of introducing polar curves? Okay, so let's describe what is polar curve first. So this is a graph. Okay. So we have two variables, right? So we should be able to write one variable as in terms of the other. So we have r in terms of theta in this case. Okay, or we can move all of them to the other side. Okay, where we get 0 on one side. So this is a typical thing. So this consists of all points P that satisfy, okay, that at least one. So just now I show you 4, right? So here say at least one polar representation. So as any one of the 4, okay, will satisfy this equation, then this is the point in this curve. Okay, so if you can satisfy the polar equation, then you are the point of the curve. Okay, so just now we have a trouble, right? So from last week, is it last week or this week? So we have trouble on describing the for example, the unit circle, right? If we write it as the function of xy, we say that x squared plus y squared equals to 1. It's really not a what function, okay? But if we consider the polar coordinate, this can become a function, this curve. Anyone can see what's the function we can define using r and theta? Okay, Y Ying say correct, good. So anyone can see what kind of polar equation we can get from this unit circle? R equals to 1, good. Okay, you can see that, you see, here, this circle become a constant function, okay? No matter what angle you give me, it is always radius 1, okay? Right, so this become a function, right? This here become a function. So it's become more convenient for us in this case. So we can differentiate the r equals to 1 function. And then let's say we want to plot, for example, if we want to plot theta equals to 1, what does this graph look like? What does this graph look like? Theta equals to 1. A straight line. Okay, very good. So this straight line, how does this straight line look like? So it form an angle from the positive axis with theta equals to 1. Okay, so you do something like this. Okay, so it seems that it can describe more thing now with a function. So this is a advantage of using polar coordinate. Okay, so I think this is a good place to stop. So let's take 2 questions before we end.
So why theta equal to 1 is a straight line?
Why theta equals to 1 is a straight line? Okay, so theta equals to 1 means what? Okay, means what? So every point, okay, every point have to form an angle theta equals to 1. Okay, okay, so by convention we will say this is 1 radian. Okay, we prefer radian over degree, so this is 1 radian. So here all the point here is angle 1 radian to the positive axis. Okay, no matter what radius, because I don't give condition on radius, right? So radius can be everything, but angle must be theta equals to 1. Okay, so how about minus? So if r positive, I think this is easier to understand, right? Because you need to form positive angle, theta equals to 1, and take all the positive radius. But how about negative radius? Okay, negative radius. Okay, maybe so if you want to consider negative radius, then it should means minus r theta, right? Just now we say that what did we say? So okay, so what did we say just now? So what is minus r theta? So minus r theta is equal to r theta plus pi, right? So if you take all the positive r plus pi, these are also your point that satisfy the same theta. Does it make sense or not?
Sir, I
Yeah,
think instead of one radian, any radian, we can also form a straight line, right?
correct. That's right.
Okay,
That's right.
okay.
That's right. So radius just help you to extend this line, right? Correct or not? So here are all the same angle, and then you can keep extending the radius positively and negatively. So only condition is the theta. Fix your theta. So you fix your theta, become a straight line. Fix your radius. You need to take all the angle. So become a circle. Does it make sense?
So the main point is if we fix the theta, so we straight away get a straight line, right?
Yeah.
Okay.
Yeah. Do you know how to get the straight line?
No, because the R is not limited, so we can assume
Yes,
any
that's
possible
right.
of R.
So you can extend the line. Yes. Yeah. One more question. Is that a way to is there a way to find a volume? Volume. So how do you find the volume of a cylinder? What's the volume of a cylinder? Pi r square times h. Yeah, I think yeah. Right. Yeah. I think you can. You can. I'm not sure is it just linear because it's pi r square, right? I'm not sure you can straight away integrate r square or not. Yt square. I think you can. I'm not sure, but I think it's similar to surface area. Because surface area is 2 pi r h, right? And then volume is pi r square h. So your r is changing irregularly. But now it's square. I'm not sure you can straight away integrate the limit. But I'll say yes now. For now, yes. You just do similar to surface area. Instead of 2 pi r, you use pi r square. So pi y square in this case. Does it make sense? Y in. Okay. Maybe I'll check first. If it's wrong, then I will tell you again. Is it normal? Okay, thank you. So I'll see you on Wednesday. Okay, see you everyone.
Okay, thank you, sir. Goodbye.
Thank you. Good night. Have a good night.